Hi, I'm Shane McGrath. I am here today to talk about transformers and universal approximators. I have a background in economics, maths, and statistics, and over 10 years experience in the data space. So I'll begin. Yeah, so here is the slides. Cool. Yeah, so the previous videos I've talked about have been about uh, papers or kind of academic papers. So this one's kind of the same. So the name of this paper is Prompting a Pre-trained Transformer Can Be a Universal Approximator. Prompting is kind of like the sequence that you kind of enter into a transformer. Pre-trained means kind of off the shelf. Um, uh, transformer. So this means that it hasn't been fine-tuned with any specific data. Can be universal approximator. So the approximation property you kind of talked about in the previous video. So this means that it can estimate a function or something along those lines, such as the example would be classifying an image that it would be able to recognize whether an image was a cat or another household animal of sorts. Cool. So yeah, the paper kind of talks about uh, various different points. Attention. Here's the main points it talks about. Attention, especially suited to model functions over hyperspheres. Um, so this is one of the mechanisms of transformers, and hyperspheres are kind of like spheres, but in higher dimensions. So spheres would be three dimensions, hyperspheres would be four, five, six, seven, etc., etc., etc. In order to do the approximation correctly, they need to be kind of they need to have bounds on them. So the researchers here kind of define these bounds in order for smooth target functions to be precise. Um, so yeah, and with these bounds, then they can approximate sequence to sequence functions um, with certain amounts of depth and length. And then finally, this is kind of the pre-trained approximation properties that the researchers are talking about, which is prefix tuning can result in element-wise functions when combined with cross-element mixing from pre-trained models and may result in may show why prefix tuning and prompting is able to approximate certain tasks. So the prefix tuning is not something I was particularly familiar with before this paper, but it um, kind of talks. It's when you kind of put a clause on your kind of prompt that is separate from the prompt itself. So usually they would contain brackets or some sort of closed brackets, but essentially it's like putting a filter on a photograph of sorts. The actual photo stays the same, but the output looks different because of the filter. But crucially the content of the sequence stays the same. Cool. So just in order to define a function, the first video I kind of talked about was the approximation property, and this worked with kind of functions. So crucially, a function maps from one domain to another domain. So here, A2 is being mapped to B1. And I say you can what the approximation property kind of looks like. It kind of it continuously approximates the function as it kind of different values are entered into the function. Um, yeah, so crucially with a function, the output has to remain the same or consistent for every time you put A2. So put A2 into to F, B1 should be the output every time you do that. So if you kind of put A2 in and you get B5 or B3 or B2, then that's not a function, or not in the mathematical sense anyway. So crucially, a function has to have a to one um, uh, uh, property, one to one being it maps from A2 to B1. And that is the definition of a function. So the researchers here are kind of trying to establish that definition through what properties would be needed in order for this to be kind of mathematically true. Cool. So this is kind of what a hypersphere looks like. As I said, it looks like a sphere, but there's many more spheres that are kind of there. They kind of exist in different in spaces, but all at the same time. Um, cool. So this is kind of what the mapping function kind of looks like, or what it's kind of written mathematically. So to the left side there is the kind of path, X being the sequence and P being the prefix, K being the kind of the number of the path. So to the right side here are the kind of exponentials. So these are the kind of matrices and the attention mechanisms. And the sum refers to the different attention mechanisms that are kind of summed together in order to get the output. Um, Crucially, these act as what the researchers say as kernels. So kernels in a linear algebra sense are kind of like a point on a in a matrices or a domain, and that is where the rest of the kind of points in the matrices or domain are kind of reflected through and this would be kind of called the core, the seed. I think that's what a kernel means, the kernel of an apple of sorts, or that sort of thing. Cool. Cool. Yeah. So you kind of just refer back to the scanning idea and the different kind of multi-layer perceptions of each of the kind of uh, uh, each of the kind of attention mechanisms kind of approximate a bit more to the kind of overall kind of sequence in order to kind of give the kind of sequence its full kind of its full output. And Yeah, and then kind of crucially, as I said here, the aim is to kind of map from sequence to sequence. So a sequence that is entered should have an approximate kind of sequence that it kind of results in, and this should be consistent. So I said the way these researchers look at it is through the hypersphere. So the approximation property that this a lot of this kind of theory is based on is kind of named as this. So this is kind of the Kolmogorov-Arnold representation theorem identifies every continuous function with univariate functions through this summing procedure. And the univariate functions can be represented as sums or compositions of other functions. So in this kind of, according to these researchers, the summing is the kind of the MLPs, the multi-layer perceptions, the attention mechanisms approximate the functions, and this is kind of the scanning procedure, and this has to be they prove this through a kind of kernels over a kind of hypersphere, as I said. Cool. So yeah, you kind of repeat the sequence to sequence. So every time you kind of enter what is a hypersphere, it should give back this answer or a very similar answer to this the, in order for the transformer to work as a proper kind of function for this sequence to sequence. Cool. And then this is kind of how it goes about it. So the kind of the previous function or the previous kind of equation that the seeing can kind of be kind of summed up to this kind of this core tension um, uh, equation, and this is kind of similar to the equation seen here with the sum the sum the sums of all the different kernels. Um, cool. So these kernels then can be seen as in the B part of it, where the f of x, the function, and the function that is kind of uh, that the transformer is trying to approximate can be seen there with the kind of hypersphere being the kind of the the point in which the transformer works, and then this kind of fleshes out through control points and kernels a kind of function, and then through different kind of numbers of control points and kernels on C, you can kind of see that the function becomes more defined and a better approximation. And then finally, and D, the the attention mechanisms are kind of um, approximate the end function. So and then this is kind of more intuition behind it, and a different view of a very similar sort of procedure through the kind of Jackson bend that they named. Um, cool. Finally, uh, the appendix to this kind of mentions spherical harmonics, which I noted that are related to a Fourier series, which had been mentioned before, and it also mentions how on the hypersphere these spherical harmonics can be used to um, sum and approximate functions. So that is worth looking at as well. I said it's a very mathematically definition kind of not heavy paper, but definitely kind of the sort of approximations or rigorous definitions that I think are crucial to understanding this kind of function behavior a lot kind of with more clarity, and how you could achieve this function behavior with transformers, and clarifying that they are kind of mathematical and geometric, and in order to get the kind of consistency that is needed for more industrial uh, use cases, then this sort of mathematical approach is kind of the way to kind of move towards that. Cool. Cheers. Thanks for watching.